Okay, then thanks for like setting this path until here, Dimitris. And I will talk about like the regression of simple type models from images. And with simple type models, I mean like simple, simpler X, Flame, and Mano, what Michael has presented before. And Dimitris has just presented like methods to recover the 3D body from an image using optimization-based techniques like Simplify or Simplify X. But fitting simple or simple X to an image is like quite limited. For instance, like Dimitris has mentioned this to some extent, like first they require like pre-computed key points. And these key points, they can be computed like with OpenPose, but they're difficult to obtain in complex scenarios and for bodies with occlusions. Like for occlusions, these key point detectors might just fail or label the key points wrong. Second, fitting a model to an image is slow, as also mentioned before. Like Simplify X in our implementation takes like a minute to recover like a 3D body from a single image, and which is quite difficult to scale then if you want to reconstruct it from a video, for instance. And finally, also these methods, they get easily stuck in local minima. Simplify X, for instance, has like different steps that are performed during the optimization. And if one of them fails or if something goes wrong, then you easily get like an unrealistic body shape or unrealistic pose. There are a lot of priors around that try to prevent this, but still it's difficult to get like a good 3D shape in general. And instead, our goal is to directly learn the mapping between the image pixels and the 3D body pose and shape using some deep neural network. And now the question is, how do we actually learn something like this? Because there are like several challenges in training such a model that one actually has to overcome. So one of the main issues is that there are just no paired 2D to 3D data, or just not enough. Like for images captured in a controlled environment, one can, for instance, obtain ground truth 3D using motion capture or some 3D body scanner, what Michael showed, what we have in our department. But it's difficult to capture really a large amount of data. And it doesn't cover like all variety that you see in the wild images. But for in the wild image on the other side, which are quite complex in terms of background, poses, shapes, and so on, like what are actually the ground truth 3D bodies? Here we see two examples where, yeah, it's not easy to just get like a ground truth 3D body for this kind of images. And another challenge is like the inherent depth ambiguity in doing the single view 3D reconstruction. They are just like multiple 3D configurations that project to exactly the same 2D configuration, but some of these are just not reasonable. Like some of these configurations might have impossible joint angles or just represent like very fat or very skinny bodies, which are just unlikely. And the first method that actually regresses directly simple shape and pose parameters from an image is HMR. And HMR uses an encoder-decoder architecture with the simple body model as a fixed decoder. And now the question is, how can one actually train this model, given that there are no or only very little paired 3D data available for supervision? And the most obvious thing is like following the image fitting techniques is to use some key point reprojection loss, where one trains the encoder to produce like a 3D mesh that best explains the 2D key points. And this is done by extracting like the 3D key points from the reconstructed mesh, projecting them into the image, minimizing the differences between the projected key points and the ground truth, like same as in the fitting. And one can train this, however, it just does not work. Like training this just leads to monster meshes, because while the recovered 3D mesh minimizes the reprojection loss almost perfectly, shape and pose are just implausible. One can add there a lot of different priors, but it's quite difficult to balance and train this. And now comes the key idea of HMR. Because even though that there are only very little paired 2D to 3D data, there are just large amount of unpaired image and 3D data. Like there are large 2D datasets with available joint labels and also several 3D scan and motion capture datasets that one can use. And the key idea of HMR is to use this unpaired 3D data to learn like a distribution of the 3D bodies. So you learn like how do bodies look, how do they deform, and then you use this distribution to constrain the 3D bodies reconstructed from the image. And this is done by adding, like in addition to the joint reprojection loss, HMR uses a discriminator to tell whether the reconstructed human body looks like a real 3D body or not. And this discriminator itself is trained on a large database of 3D human meshes, and it acts then as a data-driven prior during training. And the discriminator loss effectively reduces the depth ambiguity by encouraging the solution to be on the manifold of human 3D bodies. And one important thing here to notice is that the discriminator is only used during training. So it's only there to constrain the encoder during training. Once trained, HMR directly outputs a 3D body from a single image. And here we can see like some examples, like the video shows reconstructions overlaid on the original image, and also like the reconstruction shown from two different viewpoints to really give a better sense about the 3D body itself. And the rightmost image shows like part segmentation that can be extracted from this reconstructed simple body mesh. And HMR is quite robust and reconstructs 3D bodies from diverse images despite a large variety of body poses and the different scenes, different backgrounds, and so on. Then the next method that I want to present is like SPIN. Like SPIN improves over HMR by training a regressor with a simple fitting-based optimization as additional supervision. And for this, like the key observation is that given accurate key points, like this is key, one needs good key points and one needs a good initialization. But if one has this, then an optimization-based method like Simplify or SimplifyX reconstructs like quite accurate fits to these images. However, on the other side, like with all the drawbacks that we have mentioned, and on the other side, there are like this regression-based methods like HMR, which are quite robust, but they're just less accurate. Like the fits just don't align as well with the image as compared to the fitting result. And the main insight of SPIN is now to use these two paradigms in a tight collaboration to improve the neural network training itself. More specifically, the result of the regression is used as an initialization for the optimization-based reconstruction. So by taking this, the optimization is able to give a better reconstruction result than if you would run the fitting itself on the input image. And then this optimization-based reconstruction can be used as supervision for training the regressor. And to be more specific, like given an input image containing a person, first, like some HMR-based network is used to reconstruct like a 3D body, like the 3D shape and the 3D pose of the person. And then this regressed shape is used to initialize an iterative optimization procedure. And this procedure then fits the body model to the 2D joints within the training loop. So starting from there, starting from this good initialization from this regressor, this optimization gives a good reconstruction of the 3D body of this input image. And it's also much faster than if you would run the optimization on the input image directly because of the better initialization. And then it uses this output of the optimization and takes directly like the parameters of this and uses this to supervise the network during training. And SPIN itself is self-improving by nature because the better network estimate gives a better initialization to the optimization part and therefore gives a better solution. And then with a better optimization, with a better optimization fit, this also provides a better supervision to the actual network. Here, and one thing to also mention that this model fitting part in the loop is only used during training to supervise the actual training of the regressor. And during testing, Spin directly takes a single image as input and is fully automatic. And this video shows like some spin results obtained by running it on a frame by frame basis on this video. And despite enforcing no temporal consistency across frames, the reconstructed body is relatively stable and the 3D bodies are actually quite well reconstructed and the poses are well captured. Now one might ask, like, this just solves like this whole problem. But no, like given a single image, this regressors like HMR or spin, they reconstruct a 3D body shape and pose, but they ignore like hand articulation and facial expression. And the last 2 decades, the community has taken a divide and conquer approach by breaking the reconstruction problem down into its part, where the reconstruction of bodies, hands, and faces is typically approached severally with part-specific models. And one such part-specific model that was recently it got recently accepted is DECA, which reconstructs like 3D faces from an image. And given a single image, DECA estimates like the parameters of shape, pose, and expression of the flame head model. That's quite similar to what HMR does for bodies. And it gives additional parameters for camera, facial appearance, and lighting. And this whole thing is trained with a diverse set of losses like a shape consistency loss, face recognition loss, a photometric loss, landmark loss, and so on. There are a lot of losses involved to train this without explicit 3D supervision. And on top of this coarse face shape, DECA learns an animatable facial detail model. For this, DECA regresses a subject-specific detail code from the input image and combines this with the flame expression and jaw pose parameters that we get like from the coarse reconstruction branch. And this outputs then a UV displacement map. And this UV displacement map combined with the reconstructed core shape gives a detailed face reconstruction. And the key of DECA is that the key goal of DECA is to make this animatable, this detail model animatable. And making this detail model animatable requires disentangling identity-dependent details from expression-dependent wrinkles. And given 2 images of the same person, like everything during training, the key observation is that both should have a similar coarse geometry and similar personalized details. Therefore, exchanging the expression parameters between these 2 should have no effect on the detail code of this individual. And this is enforced as follows during training DECA. Like during training, DECA takes like 2 images of the same person and replaces the detail code of one image with the detail code of the other image. And then this detail exchange should have no effect on the rendered image. And this is enforced by penalizing the difference between the rendered image and the ground truth image or the input image. And once trained, DECA takes a single image of a human face as input and estimates a detailed 3D model of the person's head with additional detailed wrinkles. And these facial details are parameterized by Flame's expression and jaw pose parameters, which makes them animatable. And given other images with a different expression, can be of the same identity of another one, DECA transfers the expression to the first person. And then here we can see like the estimated detail shape for 3 different subjects and the reposing of these reconstructions using the previously seen 3 expressions. And actually in the paper, we show like several hundreds of images and show that this actually is robust and it works. Then another line of work like towards getting expressive bodies aims at reconstructing 3D hands from a single image. And one of the first models or first approaches to regress a 3D hand mesh from an image is this Opman model. And specifically, like Opman uses an architecture like similar to HMR to regress shape and pose parameters of the Mano hand model. But however, in practice, hands are often partially occluded by objects. Therefore, instead of reconstructing like only the 3D hand, the model jointly reconstructs the 3D hand and an object from the single image. And the key idea now of this Opman model is that while reconstructing the hand and the object during manipulation is more challenging, because of the significant occlusion of the hand by the object and vice versa. The interaction of the hand and the object potentially also simplify the problem because the physics of the contact restricts the space of valid hand-object configurations. And by jointly predicting hand and object mesh, this Opman model can reason about the hand-object contact. And this is done by penalizing the interpenetrations and encouraging contact when close to the object surface. And this results actually in better grasp when reconstructing the hand and the object together from the image. And here we see like some reconstruction results for different input sequences. And the trained model is robust to a variety of objects under diverse lighting conditions, clutter in the background, different kinds of objects, and so on. And now comes the first method that unifies this part-based regression approaches by introducing a regressor that reconstructs expressive bodies from single images. Therefore, let's revisit the goal. Like before, our goal was to reconstruct simple parameters from image. Now this changes. Now we want to reconstruct shape and body pose parameters of simple X, but in addition to this, also the hand articulation and the facial expression parameters. However, there is a fundamental problem. Like jointly predicting the body, hands, and face parameters with a single network like HMR doesn't work because it leads to mediocre results in the hand and face region. And one reason is the small size of hands and faces in the full body images, which makes reasoning about them from the low resolution image patches quite hard. But there is one thing here that we know, that running some network like HMR is still valuable because it provides like a rough initialization for hands and faces. And expose leverages as follows. Like first, expose starts from a bounding box of the person's extracted body image crop and downsamples this image to a DeepNet compatible image resolution. Then this is fed into a body network like HMR to obtain a reasonable body shape and pose estimate and a rough estimation of the hand articulation and facial expression. And then it uses this rough initialization to go back to the original image and extract higher resolution image patches for hands and faces. And since this is done like with a spatial transformer, this step is like fully differentiable. And then hand and face specific subnetworks are used to process these higher resolution part specific images conditioned on the body pose. And they predict rough, and then they predict like updates of this on top of this rough hand and face estimate. And like integrating this together, like this refines the hand and face parameters. And one thing that one has to mention, like this hand and face specific subnetworks, they are pre-trained because they're part specific. They leverage like this insights from hand and face specific literature, and they are pre-trained on like high quality face and hand images. And here we show like a video, like some predictions of expose on several in the white images. And expose gives natural reconstructions of the full body, including hand gestures and facial expressions, which is not possible by just using an HMR-based network. And this works for a broad range of scenarios, including indoor and outdoor images, as you can see here. And to summarize, like I presented 5 different methods from like starting with bodies to faces, hands, and then expressive bodies. And like first ASMR, like leverage unpaired 2D to 3D data by using a discriminator as human shape and pose prior. Second, spin integrated like model fitting in the loop to supervise the regressor during training. So it combines like the good things of model fitting and the regression parts to supervise the regressor. Then DECA learns an expression-dependent facial detail model, which can be used for 3D facial animation. This Opman model predicts like 3D hands and objects jointly, which lead to better grasps. And finally, X-pose that uses body-driven attention to regress expressive bodies, including hand articulation and facial expression from images. And now the question is, like, what is next or what is missing? Like, first, all these methods that I've presented, HMR, spin, and so on, they rely on key point information to reason about body shape and pose. However, these key points only provide very sparse supervision and therefore the reconstructed body shape is inaccurate. There is prior work that, for instance, by Sengupta et al., that additionally leverage silhouettes and synthetic data to reconstruct better body shapes, especially for images of obese people. Another point is that, like, the simple X body model is naked or without clothing. There are now methods, for instance, presented here at CVPR, that reconstruct like closed bodies from an image using some fitting-based approach. Then, as Dimitris also mentioned already, this line of work where, because images of people often contain like some form of self-contact, and the methods that I have presented did not take this into consideration. So Miller et al. Presents actually at the CVPR some method to also consider self-contact. And finally, last point, like for reasoning about humans in diverse scenarios, it is essential to further understand like all kinds of interactions between the humans and also between humans and objects. And reconstructing humans, like also multiple humans in such scenarios, with the accuracy needed to really understand the essence of this interaction is still an open problem. And that's so far it. For further details, you can also refer here to the different project pages itself. Thank you.
Thanks, Timo. We have a bunch of questions here.
Okay, I don't see them, so.
But I can read some out, or anyone else. How do you validate your results besides visually, qualitatively?
What again? Like how to?
How do you validate the results beyond visually or qualitatively?
Yeah, there are that's one problem that we skip now. This data set.
But we haven't skipped it yet entirely, actually.
Are we still on time?
We may still have time.
Okay.
Yeah.
Like there are a bunch of benchmarks that evaluate mostly like on joints. And there's also like this data set like 3DPW, where I actually showed one of the video sequences from, where there are like they put people into a scanner. So they have like a scan for each person and they have accurate tracking of these people throughout these videos. And this can be used to like quantitatively evaluate.
Let me also plug the new Agora data set, which will be presented at CVPR, which has thousands of images with precise ground truth, simple X fits to realistic in realistic images. So check out Agora. If we have time for the data set video, we'll show
then we will see this. Yeah.
In the past 2 years, we have a lot of work focused on hand-object interaction. What is the next direction for hand-object interaction? Maybe this is a Dimitris question, actually.
What is the next direction? There are a lot of next directions, I guess. But up to now, for example, we didn't have very good motion data for hand-object interaction, simply because it is very hard to acquire ground truth data. We had a recent paper at ECCV 2020 where we use a high-end Vicon system for this. And this can give people, for example, very strong pose priors that are also object-dependent and interaction intent dependent, so that you can work on this. This also gives you dynamic hand manipulation over time, so you can even learn a motion prior instead of only a pose prior. Just a rough idea. Yes, lots of room for
great, yeah. And Timo, do you assume relative tight clothing, short hair, to be close to the body, the bold, naked, simple model, or you assume an acceptable offset?
No, it's like there are no such direct assumptions made for this data. I don't know exactly what is the bias of these data sets that are used to train this. Also, like most of the work that I presented is not mine. But no, there are no direct like assumptions of this. But as I mentioned before, the body shape is not necessarily very well reconstructed. So if we see a person is very fat or a person with very loose clothing, then you can't assume that the body shape perfectly captures this.
So we do have some examples. We've done a bunch of stuff with scan data, fitting the body to scans where we assume that the body is inside the scan. And in areas where there's skin visible, it's a tight fit. Again, the Agora dataset uses that to fit 3D scans of people in clothing with simple X models. We've even done that in images, going back to the original, the Naked Truth paper, in which we assume the body is inside. If you've got a silhouette or a bunch of silhouettes of a person, the body is always inside the clothing, and it should be close to the silhouette in skin regions. So those kinds of constraints can be built into these fitting methods. Okay, there's another question. Was spin technique used in the subsequent papers like Expose? Good question.
Like we don't explicitly use such a fitting in the loop for.
But I think it would be a nice thing to do. I think it's a good idea.
I agree. We have discussed it multiple times, but
yeah,
kind of never did.
Is there a temporal discriminator model, possibly recurrent, that enforces consistency across time? Another great question. Do the GANs give artifacts in frame by frame translations?
Like for the methods that I have presented, there are no temporal.
No, but so the V-poser, for example, there is an M-poser. I think it's also public, which is a motion-based prior. And then we'll see a talk later on Vibe, which builds a temporal discriminator, exactly that. So that's in the so-called afternoon session, first talk in the afternoon session on Vibe. Domain shift is a problem for a deep neural model. For example, the model trained on sport data sets cannot handle everyday scenarios well. It seems that there is no way to get a general model. Could you share some viewpoints on this problem? Domain shift, anyone?
I leave this to you, Michael.
Well, it's a good question. So I think if you train on lab-only data, you are going to have problems. And so there's a bunch of lab data sets like Human EVA, Human 3.6M, some other ones where you get really good, high-quality ground truth because there's motion capture involved, but they don't generalize well outside. And then outside you have sports data sets and these things that are COCO, things that are hand labeled, so not so precise. So and then you have synthetic data sets. Surreal, not a very good one, older, and now Agora. And so I think some combination of all these data sets, we're seeing more and more people putting tons of data sets together and things are getting to be quite robust. Interestingly, we train on Agora, which is synthetic, but realistic synthetic, and we do better on 3DPW. So, so synthetic data sets can actually help solve this problem, which I think is an exciting direction. Particularly when you look at the Microsoft talk later, they're really pushing synthetics as a way to generate realistic training data, realistic enough to push into commercial products. So this is a viable path. The nice thing about synthetic is you can change the domain. If you want to switch from RGB to depth, or you want to switch it to infrared or something, you can just do that very easily. And then there was, Dimitris mentioned the touch paper where we do this mimic the pose idea, where we engage people in trying to help us create a data set. And if you get creative about that, you can actually get pretty good data, I think. So I think this is a really great question. Lots of interesting work to do there. to make these things really general and robust. So Timo, what's your estimated timeline to solve some of these open questions? That's a tough one.
That's, I don't know. Like, it's a good question. Probably takes a few years. Maybe we never solve it. I don't know.
Maybe unemployment will not be Timo's biggest problem.
Yes, I think none of us have to worry about all these problems being solved anytime soon, which is fun.
I see there's a question about DECA. I can see this here.
Yeah.
In the DECA paper, you used appearance model transferred from the Ball model.
I think that'll be the
Basel face model.
Basel face model.
Why did you not use the data obtained from your scanner or from your scans? That's actually a good question. Like, the main reason for it is that our scan data, like, first off, yeah, it's maybe one question or one reason for this is the amount of data that we have scanned in our face scanner, where we often scan people with like some form of pattern onto the face, which just like invalidates the texture a little bit for learning something that is. Also, our scanner doesn't capture true albedo. And for this, like for a texture model, you would want to have true albedo. The model or this albedo model that we use is not ideal, and you can be sure we will bring something better soon.
Can I detect positions of eyes, nose, hands, fingers having a fitted simple model? I think the answer to that is, well, maybe the question is, do we know where the hands and the fingers and the eyes and everything are? Yeah, we know the vertex numbers of all of those. So if you've estimated a simple model, regressed it from an image, you have the location of the eyes, the mouth, the fingers, everything, tip of the nose, whatever you need, it's there.
It's basically like this video that I showed for HMR, where the body is used to get like a part segmentation for the image. Like, one can do the same with SimplifyX, assuming that the regression result is accurately aligned with the image.
So Maurizio here has a very interesting question that I find it's a good ending question for this session. Why do you need an iterative regressor for HMR or spin? So this is a really interesting question for me because when the whole deep learning things began, people were doing classification. They were doing ImageNet classification. I thought, okay, that works great, but it's not going to work for regressing high-dimensional nonlinear problems like human pose. And but we thought, well, let's do it anyway. Let's try it. So we immediately started trying to predict human pose from images. This was with Javier Romero and an intern, and we worked on it. We couldn't get it to work. And we really wanted to get body shape. We couldn't get any better than sort of guessing the body shape. Anyway, we got some things to work, but it was really not very good. And then Chris Bregler had this paper where they regressed to the joint locations of the body in 2D. And that worked great. And then everybody started doing that. And that's when we did Simplify, because we thought, okay, we can, deep networks, they understand 2D things like pixels, and we can find joints, and so we can fit this, we could do this nonlinear optimization on top of that. But we kept trying to regress directly from pixels to pose and shape parameters, and it wasn't working. And then Ang Zhu came up with this idea of the iterative regression. So do it and then refine it and refine it again in a 3-step process. And all of a sudden it worked. And it was like rotations were just too hard. And somehow this iterative process let the network gradually figure out the rotations. And that opened everything up. All of a sudden we could do regression. But now lots of people are doing this. And I thought, so that's somehow fundamental. But now lots of people are doing it without the iteration. So there's the paper, the Center HMR paper, for example, directly regresses. There's a bunch of things now directly regressing. And I'm not sure why they work, honestly. I'm not sure what the secret sauce is that means you don't need to do this iterative thing. Might be joint, might be the representation you choose for the joints. I'm not sure. We'll see. I wish I had a good answer for it. But the reason we had it is because nothing worked until we had it. And it'd be nice to get rid of it, I agree. So we are now 1 minute over. If we skip the data, so we put together a compilation video for you of a bunch of data sets. It's on the Simple Made Simple website already, so you can, I'll put the website link in the chat.